Following on from 4.1 correlation, we're now going to look at linear regression. Okay, so linear regression is to do with lines of best fit. And a line of best fit is the linear model that approximates the relationship between the two variables in the question. Okay, so we looked at lines of best fit in GCSE. And basically at GCSE, you would use your eye to approximate a line of best fit so that you've got about even number of data points either side and it's going roughly following the trend and roughly through the middle of the data. Okay, and that looks like a decent line of best fit for that data, and then you could use that to estimate maybe the population density if you were given the distance. However, that's not particularly mathematical. There are ways of calculating a line of best fit. And one of those ways is a least squares regression. Now, you don't actually have to use the least squares regression formula because your calculator can work it out for you. And generally at A level, they give you the actual equation of the line. The least squares regression minimizes the sum of the squares of the distances of each data point to the line. Okay, so let's have a look what that means. So here I've plotted these data points onto this software here, and generally at GCSE you would do a line of best fit that looks something like that. Okay, now this goes a little bit further. Now this it looks at the distances between the points and the line of best fit. So let's have a look at the distances between them. Y on X residuals. So let's first of all have a look at the distances. So that's what showing you the distances, and the idea is that you get these to be the least possible length. However, there's an issue here because some of the data points are above the line and some are below the line. So some will be positive and some will be negative, and they would cancel each other out. So what we do in the least squares regression, like you did in standard deviation, make everything positive, we square the distances. Okay, so we're looking at the square of the distances between the points and the line. And the idea is you get the total sum of these squares to be the lowest possible value. So if we look at the status box up here, this 671 tells me the sum of the squares. So what I'm going to try and do is get that a little bit smaller. So I can see I've got it down to 623. It's gone up a little bit there. So let's move this one. So I've got it down to 593. Okay, that seems about as low as I'm going to get it. So let's check. I'm going to get this software to actually calculate the line of best fit. Okay, and now you can see that's pretty close. So the line of best fit there goes like that. The sum of the least squares was more like 586. Okay, and the equation of that line is y is equal to negative 9.848x plus 50.35. So obviously now we could use that equation to work out any value of y if you were given a value of x. Okay, let's go back and have a look at some examples. Right, so the regression line of y and x can be written in the form of a plus bx. Okay, just like I showed you there. So we've got two values which we need to work out. We've got a and we've got b. Okay, so a is the y-intercept, and this tells you what y would be if x is equal to 0. The other unknown is b, and that's the gradient, and this tells you the change in y if x increases by 1. So if b was positive, that would mean the correlation is positive. And if b was negative, that means the correlation would also be negative. Okay, so let's look at example 3 from the textbook. Okay, so in example 3, we've got some data. It's to do with the daily mean wind speed in knots and the daily maximum gust, also in knots. So W, wind speed, G, gusts. Okay, so this is the data taken from the large data set. Now we're not actually going to use that. They've plotted it for us on this little graph. So part A says describe the correlation between the daily mean wind speed and the daily maximum gust. So all we need to do in part A is describe the correlation, and you can see just by plotting that data, you can see what the correlation is. It's a positive correlation. It's kind of medium strong, so let's call it a strong positive correlation. At part B, now they've actually worked out for you the regression line, the equation of the regression line for G on W. And that is G is equal to 7.23 plus 1.82 W. So an interpretation means you've actually got to say what these values mean in context. Okay, so you need to use the variables from the question. So the gradient is 1.82, and we can say if W, or daily mean wind speed, increases by 1, what would happen to the maximum gust? Well, that would increase by the gradient, which is 1.82. W there, consistency. Okay, and then part C, justify the use of a linear regression line in this instance. Well, we can use a linear regression line because we can see from the actual scatter graph that they follow an approximate straight line fit. So we can use a linear regression. It follows an approximate straight line trend, and we've got that from the scatter graph. Okay, moving on. So obviously now we know what the equation of a regression line is. We can use that to work out some values. So if we knew a value of x, we could work out the value of y. Okay, but there's some important things we need to consider when we're doing this. Okay, important point number 1. You should only make an estimate for the response variable given the explanatory variable. Okay, so we can, if we know what x is, we can work out y. However, if you're given y, you shouldn't use the linear regression model to work out x. Okay, because of the way it will be a different equation. Important point number 2. So interpolation. So interpolation is when the value is estimated within the range of the data. So if we go back to that previous line that we did, if we were to use an x value between here and here, so the range of the data, so from about 0.6 up to 4, and we were to use that value and work out the value of y from there, then that would be called interpolation. Okay. The other thing that we could do or couldn't do is extrapolation. So this is when the value is estimated beyond the range of data. Again, going back to here, if I then tried to work out, if I had an x value below 0.6, so in this area here, or above 4, so in this area down here, we call this extrapolation. Okay, so within the range of data, interpolation; beyond the range of data, extrapolation. And we can say that interpolation is generally considered to be a reliable estimate, whereas extrapolation is not an unreliable estimate, is an unreliable estimate, and that's because we don't know what's going to happen beyond the range of data that we've collected. Okay, so interpolation, that's fine. Generally, extrapolation, should try and avoid. Okay, so let's apply this to an example here. So in this data here, we have the head circumference y on the bottom row and the gestation period of the baby x on the top row. Okay, so this is taking the head circumference when the baby is born and looking at the gestation period, how long. So the scatter graph shows the results. Here, the equation of the line is this, 8.91 plus 0.624x. The regression equation is used to estimate the head circumference of the baby born at 39 weeks and a baby born at 30 weeks. Okay, so 39 weeks would be approximately here. So you could go, actually do it. So you could go up there and across. So if you just something just under 34. So that would be okay. That's called extrapolation. Whereas 30 weeks is down here. It's outside the range of data. So that would be interpolation. So if we were to comment on the reliability of these estimates, so 39 weeks is extrapolation and estimate be reliable. 30 weeks, put it the wrong way around, interpolation. 30 weeks is extrapolation, and the estimate would be unreliable. Okay. Interpolation within the data range, reliable. Extrapolation beyond the data range, unreliable. Okay, part B. So a nurse wants to estimate the gestation period for a baby born with a head circumference of 31.6. Explain why the regression equation given above is not suitable for this estimate. Okay, so the dependent variable in this case is the y variable is the head circumference. And in this case, so using that dependent variable to estimate the independent variable is not reliable. We shouldn't be doing it from this regression line. We should not estimate the and that would answer that question. Right, that's the end of the examples. So if you could now have a go at exercise 4B.